Okay, so some of you might think I'm a genius because there was a Mars rover that landed last week, and now we've got a week later, we have a speaker about autonomous vehicles doing exploration on Mars. But the fact is that it's a complete coincidence because it takes 7 months for the rover to get from Earth to Mars. So even though I was aware of the launch last July, it completely slipped my mind when I invited Kiri to do this 2 months ago. So anyway, it's a wonderful coincidence and an exciting time, obviously. I don't remember when we first met, but I feel like I've known her since her PhD days, which were in like around 2000, 2002. What's curious, and I don't know the story behind this, but maybe she'll tell us, is that after she did the PhD in AI, she did a master's in geological sciences, and her topic was stromatolites. And this is a sedimentary rock structure that's created by microbes, and there's evidence of them on Mars. And so this is one of the reasons that people think there might be or have been life on Mars. And so I don't know if that's connected to her her JPL work or not, but anyway, she might tell us. Um, so she works at NASA's Jet Propulsion Lab, where she works in the machine learning and instrumentation autonomy group. She was also intimately involved with the excursions of the Mars rover Opportunity. That was a few years ago. And today she's going to be talking about autonomous novelty-based exploration of Mars. So thank you, Kiri, for agreeing to join us. And we look forward to your talk.
Thanks very much. That was a wonderful introduction. Let me get my slides up here. All right, someone want to confirm you're seeing the slides? Excellent. Okay, thanks. Thanks again, Rob. That was really great as a starting point for this talk. And I agree, the timing worked out perfectly. I was hopeful that we would indeed, of course, have a successful landing and that this would come after that. And that seems to be what we have gotten, which is wonderful. My personal background, as you said, I started in computer science. I'm still in computer science, I guess. And after joining JPL, a lot of my work was focused on working with planetary scientists and geologists. And obviously working with data coming back from Mars, including Mars rovers and orbiters. And so that connection to geology and planetary science was very intimate. And I felt that getting some more background myself could make me more effective in working with people who that's their primary discipline. And so that inspired going to US, getting a master's in geology. And I think that has in fact been a really good investment of time and also a great learning experience for me. The stromatolites are really cool, but there's a lot of other cool geology too on Mars. And there's just so much to learn and study. So what I would like to do today is take you all on a little journey to the surface of Mars and give you some idea of how we explore the planet and how we do that through our rovers. And what I'll be describing today is joint work with Hannah Kerner, Gary Doran, Raymond Francis, Stephen Liu, Uma Rebapagada, Sakshum Kulshrestha, Faber Nerys, and Jim Bell. So we have a large team of folks working on this with a range of backgrounds from computer science and planetary science as well. And I think that's what's making this successful. What you're seeing in the background image is one of our very first views of the new surface of Mars where our Perseverance rover has landed last week. And you've probably seen this image maybe or others like it. We're really excited because we're in a completely new place and everything is going to be a chance for a new discovery. And what I love about these images in particular is that they are the kind of image where the more you look, the more you see. So at first you might say, well, I see some soil and rocks and maybe it's actually kind of boring. But the longer you stare at this, you start to see features coming out. So there are places where it looks like there's bedrock exposed from the dust and soil. And that's really exciting because if you study that area, you can learn something about what the current location is composed of and its history. That's different from rocks that might have just been deposited there or thrown out from other locations. So this is an in situ ability to study where we are. But then likewise, some of these other rocks sitting on the surface have interesting properties, like if they show evidence of layering, which could be tell you something about past water history, how things are deposited, and potentially even the stromatolites that Rob mentioned before. Not that this is a stromatolite, but another layered structure. The rock on the left here has, looks like a lot of interesting pitting. That can be a sign of both what it's composed of. Does it have a lot of gases that were present in that rock when it was formed, or something about weathering processes happening to that rock during its lifetime? So there's like, the more you zoom in, the more you start asking questions about how these things came to be. And then beyond that, you start wondering, as you look farther out, why are some of the rocks different shapes? Why are they different colors? How did they get there? This kind of bright area on the right, it looks like maybe there's a jet blast from the rover's landing procedure that's scoured away some of that overlying soil and dust. That also could be really interesting, again, to give us access to more of what this place is made of, or maybe it's naturally occurring feature. So these are questions that pop out as you're looking at this new data as it comes back. And we actually encounter new and different kinds of objects all the time as the rover traverses to new locations. For example, with the Mars Science Laboratory rover, which has been there since 2012, here's one example of a kind of weird object that was found and highlighted because, as you can see, it's sitting there. It doesn't really look like it belongs with its local context. It's kind of a weird shape and maybe a different color even. So when this was first discovered, we didn't know what it was, and it was just called foreign object debris, partly because there was a concern that this could actually be a flake, a piece of tape or metal that fell off of the rover itself. And if that's the case, then it has engineering implications. We need to check out, did something damage the rover? What's going on? And so there was a lot of interest in figuring out what that thing was. And with some follow-up imaging, we were able to look at that more carefully and then conclude that actually we think it is just a flake of Mars rock. It's a naturally occurring object. It just happens to look a little different. So it draws our attention because it's unusual. Likewise, our rovers have very productively found several meteorites that have just landed on the surface, and we happen to drive past and discover them. Those stand out, of course, if you just look at this, by their color, but also their shape. They're kind of shiny as opposed to the dull surfaces of the dust-covered rocks surrounding it. There's some pitting, again, which can happen as a rock falls through the atmosphere, and other clues that this rock is different, right? But to date, these various different unusual objects are found by humans and by basically serendipity after the fact. Someone's looking at a picture and they say, hey, there's something unusual, let's look closer. So we wanted to ask the question, can our Mars rovers actually help us with that process of exploration and discovery? Can they help us find interesting objects on their own as they're on Mars itself? So there's a system that's already in use by our Mars rovers called Aegis, which stands for Autonomous Exploration for Gathering Increased Science. And this is a really cool capability on the Mars Science Laboratory rover, and will also be in use on Perseverance, where the rover takes a picture after it drives to a new location. It scans through the picture and looks for interesting rocks, picks one, and then autonomously fires its laser spectrometer, just like in this picture, which allows it to collect a spectrum of that surface, where you see intensity as a function of wavelength. And every single peak in that spectrum tells you that there's a certain element present in whatever was shot by that laser. So without having to drive up and touch and sample the rock from up to 7 meters away, this instrument can tell you what it's made of. And this is all happening on the Mars rover without a human in the loop. So it figures out what's the best rock, and it fires that laser and sends the data back to Earth, and then waits for its next commands. The really cool thing is that this can greatly accelerate discovery, because before Aegis, the rover would drive to a location, take pictures, and then send them back, and then shut down for the night and wait for the next day to find out what it should actually be sampling. And in this way, scientists get like a bonus observation before they even have looked at the data themselves. And it's a win-win. If it happened to be the same rock they would have picked, then they got it 1 day early, and they could consider moving on if they're already done. If it's not what they would have picked, then they can still make another choice and fire it to the target of their choice. So it's basically bonus science that totally happens autonomously. And I just realized I don't have the chat window up and I meant to add that. So hang on while I bring that up. I do encourage you, please feel free to ask questions because I would love this to be more interactive than just me talking. So I see that Matt had asked a question about using Aegis to sample one rock or shooting at a bunch before waiting for a signal. That's a really interesting question. I think if you're a scientist, you want to shoot everything, right? You want to know what everything's made of. In reality, every time you shoot it requires some energy, it requires time. You have to process the image to even select which target to use. So typically, the rover is allowed to make one, maybe two of these autonomous firings per day on its own. But there's no really engineering reason you couldn't do it more often if you have the resources. And Anna's asking, is the Mars Science Laboratory rover the Earth-based test one? Oh, I guess I should be more specific. So in 2012, we landed the Mars Science Laboratory rover, which is also called Curiosity. All of our rovers have two names, right? And that one's been driving around since then. And the Perseverance rover, or the Mars 2020 rover, which confusingly lands in 2021, right? The one that just arrived last week looks almost identical. It has a very similar physical appearance and size, but all of the instruments have been sort of souped up and made even more powerful with this new rover. And of course, as you may know, it has a helicopter on board and some other cool upgrades as well. So great questions, and feel free to keep asking them. So if it has this capability to autonomously pick out its own targets and collect data, how does that actually work? So I'm going to walk you through that process here. So first of all, the rover, again, drives to a new location, and at the end of that drive, it takes a picture. It takes many pictures, but for our purposes, we'll focus on one. And that picture is not chosen by the rover. It's pre-planned by the science team to say, at the end of the drive, I want you to look in this direction and take this image. So they have some guess of where there might be something of interest. The rover then scans through that image and finds all candidate rock targets. And then for each one of those, extracts a series of features to describe it, which are things like the size of the rock, how far it is from the rover, the intensity, and some other properties. And then filters out rocks that are maybe too far away. Again, the ChemCam laser can only go up to about 7 meters away, so it's no point ranking the ones that are too far. And also ones that are too small to be really good targets are also filtered out. Of the remaining targets then, the rover ranks them against pre-stated science priorities. And these are changeable. So the science team can say, today we want to find really large, dark rocks. So find me the biggest, darkest one you can. Or if we're interested in bedrock, again, because we want to know what the current location is made of, we want to find large, flat expanses of often bright material to be the top target. And then whichever one is top ranked, you find a target center and then fire that ChemCam laser to collect the spectrum that describes that target. And then that's sent back to Earth. And as you can see here, it can be repeated if the rover is permitted the time and resources to do that. I see there's a question about, isn't the rover driven by nuclear power and wouldn't really suffer from lack of energy? That's definitely true. It has a radioisotope thermal generator on board that doesn't directly power the rover, but instead is used to kind of trickle charge the rover's battery all the time. And it's just always putting power in there. And then the rover during the day while it's driving around, it draws out of that battery at a rate greater than it can be charged. So it can't just continually operate and maximize its activities. And it does benefit from then shutting down in the evening and letting that battery charge back up. So we carefully manage the resources, and there's a lot of testing and simulation before any plan is sent to the rover to ensure that we have margin and that we're not going to exceed the currently available power. Good question. Garnet's asking about where this computation happens. Absolutely right. This is all happening locally on the rover. And that's one of the biggest constraints from kind of the computer science perspective of what you can do. The processor here runs at about 100 to 200 megahertz. So a lot more limited than even just a desktop machine. So you don't really get access to all of those cycles for one particular process, because obviously the rover has a lot of other things going on, communications, health and safety, and just keeping itself functional. So it's a constrained computing environment for sure. And is asking, are the features typical for geology in general and tuned by the science team? You mean, I assume you mean these descriptive features that we're using here to describe each target? Yeah. Those are, as you can see, really simple things, and probably a geologist wouldn't, they would have more sophisticated characterizations like grain size and texture and so on. So here's where we had to intersect again with that computational limit. So we couldn't really employ kind of state-of-the-art computer vision to generate really complex features. So we're approximating that with these more simple ones. Great question. And then once that happens, then the science team is able, as I said, to benefit from that autonomous application of the ChemCam laser. You can actually, we've assessed here, before Aegis was available, this instrument was being used to fire about 255 shots per sol, which actually sounds like a lot, partly because when you have one target, you do, I think it's in sets of 30 pulses on the same target to go progressively deeper into it. So it's not just one shot per target. And then after Aegis was deployed, we see a lot more use of this instrument because the rover itself is making decisions and accumulating more data. And also the team became very excited about this and wanted to be using Aegis all the time. Because again, if you can get extra bonus observations, then why not? And that's right, a sol is a day on Mars. We don't say day because technically it's not exactly the same length as an Earth day of 24 hours. It's a little bit longer. So this is the more generic term on any planetary body for the time it takes for the body to go around once and you get the sun back in the same position in the sky. So here's a map of where Aegis has actually been deployed as the rover is driven across the surface of Mars. And when I say the rover, I mean the Mars Science Laboratory Curiosity rover. In Gale Crater, it's been, as I said, used a lot to acquire these new samples of new targets and helps us with accelerating exploration, because then you might be able to move on and drive to your next location sooner because you've already gotten the data you would have wanted to get, but would have taken longer without Aegis. And it's already on board with Perseverance. And once the SuperCam instrument starts operating, we start driving to new locations, we'll start getting this kind of data back from that instrument as well. Currently, as I said, so Aegis allows the science team to express their science priorities. And currently that's often to find large exposures of bedrock. Patrick's asking, I think, about whether we have search parameters optimized for life search. I think, so for this particular application, no. So where it's really focused on geology and understanding the composition of the planet because we're specifically looking for rock targets. There are actually a lot of scientists on the mission with other interests, such as looking at soils, atmospheres, and of course, past habitability is a huge priority of the mission. But the way Aegis is being used right now is really focused on how are you going to sort these different rock targets. I think if we wanted to get at the habitability question specifically there, we would need more complex features to represent the rocks that we're prioritizing. And often some of those fine details, especially if it were kind of past microbial evidence, like with stromatolites, you wouldn't get that out of these coarse wide view NavCam images. That's something you get from the close-up, high resolution, multi-wavelength kind of follow-up images as well. Anna's asking if the number of shots per sol is part of the onboard calculation or preset by the science team. The plan definitely dictates, it tells Aegis you can collect one more target, which might be, as I said, 30 individual shots, or you can collect 2 targets. And that's kind of the extent right now that the rover is told how many it's allowed to acquire. And also if, because we don't really control everything, if the rover was told to drive somewhere and somehow it took twice as long as planned, it runs out of time or energy, then it won't just blindly do this action. It will only do it if it's safe to do so. So there's a lot of safeguards there. Garnet's asking about navigation. Yes, when I say NavCam, that is actually the navigational camera on the rover, and it takes those pictures as it's driving, maybe every half meter or however frequently it needs to safely navigate. There's some autonomous driving capability, which I'm not even going to talk about today, but it's also very cool, that allows the rover to find a safe path through a rocky area to get to the endpoint that the team has chosen. That's why when I alluded earlier, it could take a drive could take longer than you think if there are more obstacles or it has to adjust. So definitely navigates visually. It knows where it's trying to get to, and then it can assess hazards in front of it as well. So back to our question of, okay, we know the rover has the ability to find interesting like bedrock or whatever the current science priorities are, but what about the things we don't know in advance? Nobody's had pre-coded to look for something like this, but when it comes up, we still consider that valuable. So we've been looking at taking the same process and just plugging in a different ranking capability here in this orange box. Instead of saying we want to find the things we know are valuable, you can have the option of saying, oh, well, look for what's most unusual in this new place the rover has driven to. So the way that works is, again, you take this navigational camera image of the new site that no human has seen yet. We use this automated system called Rockstar to find all of the candidate targets, extract features, and then normally that would go off to Aegis to pick one to shoot at. But we can also say, let's do novelty detection, leveraging targets from all of our previous solves to say what's most different from what we've previously seen on Mars, and then prioritize that way. And here's some example output, but I'll go into what all that means a little bit later. So going through these steps then in order, how does that work? Finding the targets, again, we're in a computationally limited environment. So we're not using a CNN, we're not using a region proposal network or anything that you might think about doing with state-of-the-art here on Earth. We have a really simple procedure that runs quickly enough to run on the rover, where first you take your scene and you do edge detection to get these edges around the various rocks, and then do some basic morphology to fill those in and find closed objects, and you extract then their contours, and those become polygons that outline hopefully individual targets. And each one of those becomes an opportunity to be collected with the ChemCam laser. The representation we talked briefly about before, I want to give a little more insight into that. For our study of novelty, we weren't sure what features would be most appropriate. So we looked at some different ones. First of all, kind of as a baseline, just using the pixels themselves. So you just have this rock target, you have a 64 by 64 image here. For this, you need to then resize all of your targets to the same image size, so you have a consistent dimensionality of, in this case, 4,096 pixels. And that's one place to start. You can aggregate that information to describe a target with fewer features by just getting some statistics over the intensity values, the minimum, maximum, and so on. And then also, this is what the Aegis system is actually doing, using intensity properties, but also doing an ellipse fit to each target, and then figuring out what's the orientation of that target, what's its eccentricity, and some other shape parameters to give you more than just intensity out of it. We wanted to look at which of those three representations might be most effective. Then moving on to the core, which maybe is the most interesting from kind of an AI perspective, how do you actually score the novelty of a new rock? So here, I'm going to describe 5 different approaches that we were comparing to doing that, to assessing what is the novelty of a new item X with respect to what we've seen before. So one simple way you can do this is using a principal component analysis decomposition of your previous targets to get a low dimensional representation of target content, and then see for your new item X, how is it different from what we've already seen? So the way this works here, we have our new item X, which is represented by its feature vector. We subtract off the mean of everything we've seen before, and then project that into our principal component vectors, and then try to reconstruct it back into the original feature space and just take a difference between those two to see what may be different or new. It's a little easier to think of this visually. These are not Mars targets, these are people faces, but I think it's a good way to illustrate how this works. You have some large number of images, you apply PCA to get, in this case, 4 principal component vectors, which can be represented as images themselves, each one. So you can think of these as highlighting different key properties of, on average, human faces in this data set. And that means that any individual image can be represented as a weighted sum of those 4 components. And if you have these weights and then you add them back together, you get some kind of reconstruction back into original feature space that corresponds to these weights. And that's what this orange box is here. And if you compare that to the original image, you can see what was lost, what was not reconstructed. Here, one of the major things that wasn't reconstructed very well are the glasses, probably because they're a fine detail and because they may be rare within the data set, so they don't emerge as one of the top 4 properties. So that difference tells you that something new has happened. And that's how we quantify reconstruction error as novelty. If he were not wearing glasses, then he would have probably a lower novelty score. We also looked at a variation that uses that same approach, but modifies it so that you can incrementally update your model of what's known, those principal component vectors, using the selections you made earlier. So that way you don't give a top ranking to 5 copies of the same thing just because it was novel once. But after you've seen it once, then it becomes known and you move on to different kinds of novelty. Secondly, we looked at novelty using a really basic, commonly used algorithm called RX for Reed-Shalley that generates a background distribution from your previously known data and computes how different your new item X is using Mahalanobis distance, which relies here on the covariance matrix. So you can see that the math we're using, again, has to be really simple and straightforward to be something that can be computed on board a rover. And we also looked at a local version of that instead of comparing the whole image vector X to whole image vectors in the past, we'll instead look at local differences for sliding window across the image, comparing what's inside that square to the ring around it. And this can be much more sensitive to local anomalies instead of saying the whole image has to be different, but if it has some smaller different property within it, you can detect that. And finally, we looked at an approach called the isolation forest, which some of you may be familiar with, which is a process of growing a forest of multiple random binary classification trees from previous targets. This is a completely unsupervised approach, so you don't need data labels. But what it does is randomly picks a feature like the Y feature here, and then randomly picks a threshold like A and draws a line. And that becomes the first split of this tree. And then it randomly picks the green splitter, and then randomly the orange. And it keeps doing this until it chops up all of the space into discrete isolated areas. And then if this item can be reached with only 3 splits, then it has a depth of 3 in this tree, and it is considered a very novel kind of observation, because just randomly dividing the data up, you very quickly found that it was on its own. As opposed to if you have some point near the center here, this takes 11 random splits to reach that point and isolate it. So that one would have a lower novelty score. And then for the isolation forest as a whole, you just average those individual scores across the entire ensemble, and that gives you an estimate of how novel a given item is. Patrick's asking about the axes. These are arbitrary, that's why I didn't even label them. This is just a 2D example of what you can do with an isolation forest. If this were real data, we might imagine these are 2 of the features that we extracted, like maybe area and intensity or something, but it's actually operating in the full dimensionality, not just 2. Then finally, after you have given a score to every target, you can select, in this case, I'm showing the top 2 in these colored boxes. boxes that are selected by each algorithm. And the squiggly polygons that you're seeing are the actual contours found by Rockster as the target. They weren't drawn by a human. That's why they're maybe a little bit squiggly. But a human, out of all the targets in this image, picked those two as being novel, because you can't see because of all the overlays. But if you zoom in, there's plate-like layering happening. And again, layering can tell us something about how these things were deposited in the past and possibly the potential for water being there in the past. So in this case, we see some good agreement between the novel ones chosen by a human and also the ones chosen by the algorithms. And interestingly, though, there's this target 3 that was chosen by our novelty systems, several of them, but not by a human. So we looked closer to this, and you can't tell probably, but it's actually a rather large rock here, but it's almost entirely covered in dust. And so it's half buried. And this part that's exposed actually shows that same layering that's of such interest in these two rocks, but really hard to see because of the dust covering. And so it's a more subtle indicator, but not surprising that the algorithms also picked that one out. And here's another example where the novel target, although it looks small and kind of non-distinguished, it's a flat exposure of bedrock. There's a theme, right? That's an interesting thing to find. Often everything's covered in dust, so we like to find the bright exposures of this more pure bedrock. And the Aegis algorithm, which is the white squares, definitely found it, but that's what it's tuned to find. A lot of the novelty algorithms also selected this, but they're picking some other items too. So this is a chance for us to compare them and see how often do they agree with human judgments? Do they find something new? So I just showed you a couple of illustrative examples, but we did this same process over 28 different scenarios where the rover would take an image. Well, we have the images that the rover took historically, and we can simulate on the ground what it would have done if it had the capability to do novelty assessment on board with its own history of previous selections. So the goal was to rank all of the targets within an image, and we allowed the algorithms to select their top 2, and then we compared them to human judgments that were independently done by a member of the science team, so we would be separate there. What you're seeing here is for each of the 5 algorithms, each have a performance level based on how many novel targets they found over that collection of images, and so higher is better. And one good thing is that all of them definitely outperformed random selection, and interestingly, random can often be kind of good at novelty selection just because it's unbiased and it can find things. So we were glad to see that it did better than that. And we include the Aegis performance level here, not because this is a competitor to Aegis, but just to show that we are adding a new capability. So Aegis is not designed to find novel targets, but if it somehow did a really good job, just coincidentally, then we wouldn't need a new module for that capability. But overall, what we found was, interestingly, the isolation forest with the intensity and shape features combined did the best, although these differences for these top bars are only off by 1 or 2 across the data set. So actually what we might conclude more is that each algorithm has an optimal set of features that seem to work best with that algorithm. And all of them have some ability to find novel content. And then it comes down to resources, computationally, which ones run faster, which ones take longer, and which ones take more memory. And I'll talk briefly about that too.
Before we leave this slide, how often do 2 humans agree about novelty?
Great question, Russ. I just now seeing that in the chat. We have not assessed that, and that's always important when you're comparing to human judgments. So I think that's a step we need to take next, certainly, to see where would they, I would hope it would be pretty high, but we don't actually know. Novelty is notoriously a difficult thing to objectively quantify anyway, right? And even within the science team, there will often be debates about which target we should go see next because people have different internal priorities. In this case, Raymond Francis is our collaborator on this work, and he's on the ChemCam science team, so he has the sort of mission history, and it can, with the the ability to look back. He can say, oh, that target ended up being really interesting later. So we have some validation that this is a novel the first time we saw a particular feature. But certainly I would love to add 2 or more additional independent human inputs here.
I was also wondering, when you compare to the data set for novelty, is the data set composed of everything that the laser has been shot at, or just every rock that appears in every image that's been taken?
Yeah, because you might get different results depending how you define your previous data set. This, in our case, we're using all of the candidates that Rockster found from previous images. So not just the ones that ended up being chosen and fired upon, but the whole set. Somewhat limited in that we were just working with the images. Remember I said for Aegis, the science team pre-plans what that image will be that it gets to analyze. It doesn't actually analyze every NavCam image that the rover collects. So it's definitely a subset of the rover images as a whole, but they're all of the ones that were designated of interest for the Aegis system to tackle. And in addition to, so these overall numbers, like I said, at the top, they're kind of similar, but the targets they're actually finding are different. So I picked out some targets that were uniquely found by a particular algorithm, such as this one. So LRX was the only novelty algorithm to find this bright vein that's being exposed. Again, because it's very sensitive to smaller or more subtle or localized novelty. And the rest of the algorithms had to, they used the information over the entire image. And so maybe it didn't emerge as a top candidate. So this is definitely what we would expect as a particular strength of the LRX local approach. And likewise, these targets were only found by the isolation forest, where we see a network of veins popping out from these 2 different rock surfaces. And that's really interesting because it tells you, again, something about mineralogy and potential past of how this rock was formed. Whenever you see veins, that usually means some kind of fluid was flowing through there and depositing minerals. So it's not just a rock, but it's actually a rock with a history. And the isolation forests seem to be pretty good at finding those specifically. Now, all the examples I've shown you so far are from grayscale images, and you might be kind of wondering about that. That is the format that the navigation camera takes its image in. So one exciting thing about the new Perseverance rover is that it does have color navigation cameras. And so one of our questions also was, does having the multi-band RGB image, does that help you do better? At the time we were doing the study, we didn't have any images from Perseverance to compare directly to. So to do that, we used a grayscale image from the navigation camera and compared it to a color image from the mast camera. These are both from the MSL rover of roughly the same location and target, although you can see the zoom levels different. These were one of the closest matches we could find. And if you look in grayscale, here I'm just showing the Aegis selections in white and one of the novelty algorithms, just for clarity, in purple. None of them find this big rock sitting here, which is a meteorite, which is definitely of interest and unusual, and I think draws the human eye immediately. Turns out, though, it wasn't even found by Rockster as a candidate, which is why it never got ranked. The little gray boxes you're seeing here are all of the candidates in the scene, and it's not appearing. Probably because it's partially, again, covered with some dust, which, if you look closely, means you can't close a contour of a sharp edge around this object, so it fails the initial selection of candidates. So it didn't even get ranked. But when we move to color, it definitely emerges as a target we can rank. In fact, it has multiple targets on it, and it's chosen both by Aegis and by the novelty detection system as being an interesting target. So we have evidence that the color will actually help us find targets better. We also suspect that it can be helpful for compositional novelty, not just, oh, this one's brighter or darker than what we've seen before, but maybe there's something in the wavelength itself, even just with 3 bands, but ideally with more, that can show us something about novelty. So finally, I want to say something about the world in which this code is running, because it is so different from our desktop or cluster computer or whatever you typically use for your data analysis. It's a really different world living in an embedded system that's running on a rover. So one constraint is the physical distance from Earth to Mars, which it varies depending on the two orbits and the time of year. But right now we're at about 134 million miles away, or 250 million kilometers, depending on your flavor. And that induces a 12-minute communication delay each way because of physics, right? The speed of light is finite, and that's the quickest we could actually receive data from Mars right now. And that's only if you had continual coverage, which we don't. The deep space network that talks to all of our remote missions has to share time between rovers on Mars, orbiters on Mars, all of our missions to the outer planets, to the sun, and to everywhere else. So each mission gets a time slice, maybe 1 to 3 communication windows per day for these rovers. And so they have to kind of bundle up their data and save it and send it back. So nobody is commanding these in real time ever, basically. And the amount of data you can send back each day is limited. The amount of computation you can do on board is limited as well. The processor, as I said, runs, say 100 to 200 megahertz. And it's one reason for that is that it's a radiation hardened processor so that it can withstand the adverse computing environment in space and on the surface of Mars, where radiation is much higher than what we have on the surface of the Earth. In addition, these algorithms are given maybe 16 megabytes of RAM to run in. So they can't just consume as much memory as we might just natively do here on Earth. And empirically, we've found for the Aegis system, which is currently ranking those targets, it takes it about 2 to 8 minutes to process one image. So that includes the acquiring the image, and actually it's 2 images, so you get a stereo pair. And then you have to do a stereo calculation that gives you the distance from the rover feature, which is critical for filtering out the ones that are too far away. And then finding all the targets with Rockster and so on. And as you can see, the number of targets found influences that runtime, which makes sense, almost in a directly linear pattern. These dashed horizontal lines indicate 1 minute, 2 minute, 3 minutes, 4 minutes of total processing time. So you can't take all day, you can't shoot every single rock, but we can quantify and live within these resource constraints. Another interesting aspect is that there are flight coding rules that restrict the kind of code you can actually write. For one thing, and this is one of the big ones, there's no dynamic memory allocation allowed. It's simply considered too risky to allow an individual process to start allocating as much memory as it might want in ways we can't predict. We would hate for it to starve out some critical housekeeping process on the rover, for example. So up front, each algorithm must declare and allocate a static block. This is the maximum I'm ever going to use. And what that means is that internally in your program, you have to then manage your own memory effectively and decide how you're going to use those bits. And that adds some additional complexity to the programming process that some of us may not have had experience with before. And I think it's an interesting constraint to be aware of. There is actually a lot of other coding rules as well, but that's the big one. So right now we are embarking on that process of doing real benchmarking with these 5 novelty algorithms to assess their runtime and memory consumption to make that case for, okay, we know how they perform, but which ones are going to be the most efficient and feasible for the onboard setting. We're running these algorithms, so we're porting them from Python to C, first of all, and then we're running them both on a standard Linux workstation at, say, 3 gigahertz, as well as a PowerPC 750 board that runs at 300 megahertz, much, much closer to what the rover's CPU is actually capable of. The only difference being it's not radiation hardened. So that's why it's a PowerPC instead of a RAD 750. It also runs the VxWorks real-time operating system, which is not Linux, but is what runs on the rover. And so that's what will allow us to assess in a more realistic setting, how long does it truly take to do a PCA? How long does it take to train an isolation forest? Is that feasible? So to conclude, what I've described is 5 different algorithms that we've evaluated on 28 different scenarios so far. And if you just look at the performance numbers, the isolation forest with intensity and shape feature seems to do the best, but we have good fallbacks with at least 3 other algorithms using just basic pixels. It will depend a lot on what we do, what we find with this benchmarking effort to figure out what the resource consumption is. We're also looking at not just RGB, but multi-wavelength images, since the mass cameras on these rovers can take images that extend into the near IR. And that tells you a lot more about composition, not just the intensity and shape. We're pretty excited about what the capabilities would be there. So I'll stop there and take additional questions, but thank you for your attention.
Thanks a lot, Kiri. So first, I have 2 questions. One's really simple, as I know we've talked face-to-face, but I can't remember where that was. It could have been at Houston or in California or at a conference, but I think it's the pandemic and the old man's mind that are going. But with that context, thanks for joining us, because it's really nice to have you doing this for us. And I want to compliment you is that my first encounter with you face-to-face is that you speak with great clarity, and you continued that tradition for all of us. So thanks for that.
Thank you.
The second technical question is that there is a lot of new activity in AI and machine learning regarding what some people call continual or continuous learning. And I was really happy on the slide that was about the novelty detection, you not wanting it to become habitual, I guess is one way to describe it. And part of the answer to my question comes with the constraints you face in actually getting any computation done and data moving back and forth from such a long distance. Have you considered or done any work on optimizing, on developing heuristic measures that can be used to help optimize that continuous or continual learning to hit the right sweet spot on not being stuck in a habit rut of what's novel?
Yes, great question. I think you're alluding to when I was talking about this incremental update to the model.
Yeah, absolutely. Yeah.
That's right. Yeah. Not explained here, but actually critical to any use is that you have to decide what K is, how many principal component vectors you're going to use to represent the variation in the data. So the larger that is, the more details you're going to store as like normal or past. And the smaller that is, the more coarse your assessments will be.
Yep.
So you're more, yeah. And so we don't know what the right answer to that is truly. And I think it's useful to leave that as a parameter so we can explore that. And we haven't done that range, that sweep over this particular assessment yet.
Okay, so that's something that would make sense when you finish or when you get to a point where you've hit a milestone in the assessment of the context and algorithms, and then say, which of these could benefit with a broader window of data assessment and give us higher value and novelty. Okay.
That's right. And there's also an implication for runtime there. So if you choose K really large, you're taking more memory, you're probably taking longer. And so we have to assess both of those. Great question.
Okay, thanks a lot. And thanks for giving us this talk.
Thanks, Randy.
So if I can ask another question, you talk about, so one of the challenges, of course, is how do you evaluate a novelty algorithm? So one approach you match humans, but maybe that's what you don't want to do. Maybe you want to find things that a human wouldn't have found that will downstream, lead to life or lead to whatever else. I don't have an answer, but the solution of saying I want to match people sounds like it may not be the right thing to do. How do you go about addressing the question of how do you evaluate the quality of a novelty algorithm?
Yeah, that's a great question too. So the human judgments we're using here are just a proxy because that's kind of a place to start. But there are other things we can certainly do. One would be looking at agreement. So if you have 5 out of 5 picking a target, even if a human didn't pick it, you probably want to look more closely, more like an ensemble. If we had have the resources to run all 5, I definitely would recommend that. But secondly, another thing we've talked about, this is still kind of on human judgment, but it's more representative of the science team, is when we first see a target in a NavCam image, it's maybe the first time it's been observed, but historically we can look forward because we have the whole traverse now up to now. and see if that target happened to be later chosen by a human, even though we don't have every human's choice. We can look at what the instruments were used for later and project that basically to say we should have found this sooner. And then finally, going beyond the current human judgment would be run this over the whole archive and have a human look at its picks kind of the other way around and say, oh my gosh, we didn't even notice that, but now you're showing me a totally new discovery. I think that would be extremely valuable too.
Or say the one that actually found life on Mars, the novel we thought in the that was the one we should have been using, but I appreciate it's hard to do that at this point.
Yeah, we don't have any examples of life on Mars yet, but
Because wrong novelty algorithm. No.
because
That, I
what?
appreciate because we're using the wrong novelty algorithm, perhaps, but no, I'm not thinking so. No, it's a great
Yeah.
talk, very interesting things to think about.
Thanks, Russ.
Thank you.
I noticed there's a couple questions in the chat I did not address as well, so I'll just quickly comment on those. There was one question about, yeah, why are all these, the color image has all these different candidates. It's clearly more populated than the grayscale. That kind of jumps out, right? And why is that? Well, we believe the reason for that is the Rockster algorithm has a set of parameters and a profile as well, and it was tuned for the grayscale environment. We're applying it here on the color image a little out of its area of expertise. And we've discussed whether we need to re-optimize those parameters so that it can be tuned for a color image. We haven't done that yet. So that's also, I'm glad you guys are watching so carefully here. And Candy asked about the rovers using advanced edge computer effectively, if you want to think of it that way. Are there lessons applicable to the Internet of Things? I love the thought of the rover being part of our Internet of Things. In some way, you can think of it that way, right? It's an intelligent device that's way out on the edge, far away from us, and is carrying out our desires and helping us explore. I feel like a lot of Internet of Things considerations aren't operating quite as in a hospitable environment as the rover, so I don't know if the exact same lessons apply. But it is definitely that remote operation needs to be fully autonomous almost. And I'd love to see connections made there. So thanks.
I had a question as well regarding, again, the novelty detection. I was wondering if you've thought of it all, or if it would be possible to have some sort of supervised or reinforcement learning technique, and then you just have that pre-trained, and then you're only doing inference, which isn't necessarily too expensive depending on your model, or if it's an issue because there's just not enough training data. And then I guess connected to that is, are there any environments on Earth that are kind of similar that could be used to gather data related to novelty detection or test out algorithms here, like deserts or something? They have similar features.
Yeah, again, novelty detection is kind of specialized. It's not necessarily something you can train for, because the whole point is that you want to find the things you don't know about. We have been looking at an algorithm called negative sampling, which gets at that a little bit. It's a supervised approach, but it's like self-supervised. It has a collection of the past or the known or the normal observations, and then generates synthetic observations that are outside of that manifold or that space, and then trains a binary supervised classifier to distinguish them, with the hope that when you do encounter real novelties, they'll fall into that negative space that it's already been trained and optimized for. We're just now starting to get some results on that one, so that's a new thing. I would say though, it feels like, I think to a lot of us, that if you're exploring an environment, it's an obvious mapping for reinforcement learning. Like that's kind of the goal is let's learn, explore. How do you trade off looking for new things versus exploiting what you already consider valuable? And in general, that's probably not feasible for a very expensive, unique one-off rover in a new environment, because the risk of making a poor choice could be high. Now, if it's exploration in the sense of what data you collect, the risk seems a lot lower than exploration, for example, for the autonomous navigation system. So I think that's a conversation we can continue to have. Largely to date, we've really been constrained by that computational limit. So that is also something NASA is strongly pushing on. there's an effort called High Performance Space Computing, HPSC, that's aimed at getting us our first multi-core processors, and then ultimately even potentially GPUs, which would just open the floodgates for more capability on these rovers. Matt, I see you have your hand up.
Yeah, thanks, and love the talk. So it seems like if you're just zapping stuff with a laser based on novelty, you might get in trouble, because as soon as you see the green alien, you're Martian, you're going to zap him. But more seriously, what if there is a piece of tape, or what if something's going wrong with your camera? It seems like if things are too novel, you may want to raise up a flag and do nothing. Am I thinking about that the right way?
Great question. I'm almost surprised now that no one's asked us that from the rover team so far. I think you could definitely build in some safeguards. The rover already has multiple. For example, it's not allowed to shoot itself. And that sounds really basic, but rover hardware is very novel on the planet. You know, it's not naturally occurring. So when it spots, like over here, parts of itself, it natively zeroes in on those immediately. So we use a mask to protect the rover hardware because we know where the rover physically is. So it's not allowed to shoot itself. It is also not allowed to shoot the sun, which also seems kind of weird, but the sun can actually damage the spectrometer. So we don't want to point it directly at the sun. So you could add some additional, I think some additional rules in safekeeping if you felt like, hey, the novelty score gets too high, we need to reconsider if the laser, the action of collecting data could have some implications. Although we talk about a laser, it's actually objecting like, you know, microns or really, it's not actually drilling holes into the object, although it sometimes looks that way. A lot of times it's puffing away overlying dust, so the holes look even bigger. It's really just ablating and turning into a plasma, just the top tiny little amount of that surface. I'm so glad you asked that. Someone's going to ask me, I know, from the mission. So thank you.
Does it see its own tracks? Does that look novel?
Yes. So tracks are definitely can appear novel. In this case, we would probably not see them because they probably wouldn't show up as a closed contour object, because that's what the Rockstar is trained to find is, you know, objects. But if we allowed it to look at all the textures and all of the surface locations, then I would agree on that one. And weirdly enough, that could actually be valuable because sometimes the tracks expose subsurface deposits of minerals, and it's really great to get a sample of those. That's happened.
I know that's listening also. If something sounds funny, will that make a difference?
Ah, yes. Perseverance is the first one to have a microphone.
Yeah.
I don't know if some of you have listened to it. They have an audio of the landing, or no, of it sitting on the surface. You can hear the wind whistling by.
Yeah.
We haven't looked at finding novelty in that to date, or other modalities of data that are being collected, but
I'm not sure what you do with it if you did. That's novel, but
yeah, I don't know. Maybe just send an alert.
Kiri, I'm going to cut in here. I know you've got some one-on-one meetings and you may have other things to do. So I think that the discussions and the question could go on forever. I've even got one myself, but I'm not going to ask it. So so maybe at this point we can stop the general meeting. And yes, thank you very much for giving the talk, and I really appreciate it.
Thank you. And yeah, if anyone has follow-up questions and you don't have a chance to meet with me or talk, I'm going to put my email here in the chat. I totally welcome any questions you want to just email me. I love to have this conversation.
Okay, bye.
Thanks very
Take
much,
care.
Kiri.
Okay.
Thank you very much, Kiri.
Thanks for coming.